this when I did the call for paper selection, we got a lot of good submissions, and this one came on the spot because Windows is still the majority of the operating system out there, right? Microsoft Windows, and this is exactly what it's all about. So it's about replay attacks on WinReg RPC clients. So I'm very happy to have you here, Steve. He came from Israel, had a long flight, especially just for come here to Bergamo and presenting his research. So that's make me very happy when I have like people that voluntarily go into a long flight and travel for hours to come here. So let's make a bit of thank for our speaker. Stage is yours. Good luck. The mic.
Okay, can you hear me? Good?
Yes.
Okay. So thank you for coming. I'm very excited to be here. Thank you for coming for my talk. Hope you're enjoying the conference. I am. So yeah, today we're going to talk about, the talk is called Call and Register. Okay. The talk is called Call and Register. Basically, it's an NTLM relay attack that I found on the Windows Remote Registry RPC client. Yeah, it's a lot of words. We're going to go over it and break it down pretty soon. In terms of our agenda for today, we have an introduction, overview of what MS-RPC is, how it's implemented, and how it behaves behind the scenes, because we need to know what we're dealing with in order to be able to attack it. Specifically, we're going to look at how RPC interacts with authentication in Windows, and more specifically with NTLM, because that's what we want to relay. Then we'll see our victim, the Windows Remote Registry RPC interface, and see how we can implement a downgrade attack that allows us to have an NTLM relay attack on it. Before we start, just a bit of who I am. Just a bit of who I am. I'm Steve. Hi. I'm a security research team lead at Akamai. I've been at Akamai for nearly 5 years now. Done a lot of roles there. And in the last year, I'm managing our research team. Over the past years, our team has done a lot of research on RPC and MS-RPC specifically. We found multiple attack surfaces, vulnerabilities, and present them in multiple conferences. And this is another step in this journey. And for that, let's see what's RPC. RPC stands for Remote Procedure Call. It's basically a way for processes to share capabilities with each other without having to load new binaries into each process memory space. It's not something that's unique to Windows. You have RPC implementation as a standard and across multiple domains. Google also have their own implementation of RPC, etc. But specifically, we're going to talk about MS-RPC. MS stands for Microsoft, obviously. It's Microsoft's implementation of RPC in the Windows ecosystem. And it's a very integral part of it. Stuff from the service manager to the registry, to netlogon and authentication in general, everything is implemented over RPC. So it's very good to know how it works and how it behaves, even if you don't really care about the remote registry relay attack. So to understand RPC, we need to understand its unique terminology. So we have the RPC interface, the IDL and MIDL files. We have the transfer protocol, the endpoints over the transport, and the RPC binding. So let's dive into it. RPC works in a client and server model. A client wants to call some functionality that is available on the server. The client and the server are both processes. They don't have to be on the same machine. They could be over remote machines. There's support for both of that. But how does the client know what does the server extend, or what capabilities it has? For that, we have the IDL, or Interface Definition Language. Basically, it's a form of textual representation of all the capabilities that the server extends. It's found in a unique file with the IDL extension, and inside we have the interface name, which is what we can use like WinReg or Remote Registry. It has a unique identifier, a UUID, which is what the RPC actually uses to identify instead of just textual-based names. And inside, we also have all the function declarations and any data structures that they might require. But that's an IDL file. How does it get into the binary? For that, we have the MIDL, which is like a compiler or transformer that Microsoft implemented that takes the IDL files and converts them into C header and source files for both the client and the server, which can then be compiled, of course, into those binaries. On the client side, just a wrapper that handles all the RPC logic. And on the server side, we have a wrapper for RPC logic and also a jump to the actual server logic that implements any capabilities. But for communication to pass and for calls to go, we have to somehow send the data over. For that, we have transport protocols, and endpoints are what we connect over those transports. So we can have TCP as the transport protocol, and an endpoint will be a port number. Same with UDP. We also have named pipes over SMB, which are very common. And then we have a pipe name. And we also have here a few more examples like ALPC ports, which are only local, HTTP, or Hyper-V sockets. Now, it's important to remember that what I have on this table here are what is commonly used today. The RPC standard has around 14, if I remember correctly, protocols. Most of them are obsolete. And Microsoft specifically, they're all documented, and Microsoft specifically mentioned to not use them. And remember this tidbit because we're gonna see it a bit later. Endpoints can also be well-known or dynamic. In the case of well-known endpoints, they're well-known. Both the client and the server know what the endpoint is in advance. It's part of the endpoint definition, the interface definition, and they can just communicate immediately. With dynamic endpoints, neither the client nor the server know what the endpoint actually is. The server gets it allocated dynamically, just like you have a random source port in TCP, and the client has to somehow find it out. For that, we have the endpoint mapper, which is an RPC server in it by itself, that implements this. So the client communicates with the endpoint mapper over the well-known TCP endpoint, TCP port 135, which is the port that is most commonly associated with RPC traffic in Windows. So the client communicates with the endpoint mapper, requests the endpoint of the server, gets it, and then they can just communicate normally. And this is just some examples of RPC interface documentation taken from MSDN. We can see a few examples of the differences in documentation. For example, the task scheduler doesn't have any associated endpoint, while the service control manager has one, named pipe, and the encrypted file system has two. There's no really rhyme or reason about why something has multiple or no well-known endpoints, but it's just something that we need to know when we want to interact with RPC interfaces. The best solution is, of course, always use the interface UUID, because that's what is always going to be constant. In terms of how it looks like over a network, we have multiple steps. Of course, the first step is a TCP handshake between the client and the endpoint mapper. Then we have an RPC call and response for a map request. You map an interface to its endpoint. And we can see here in the response from the server that we have a TCP port. It could have been a named pipe. It could have been anything else that is supported. And then we see a TCP handshake between the client and that port so that the client can send an RPC request, this time for the service control manager. Now, you might have noticed I skipped two parts in this pickup, and those are the binding, because I want to focus on it a bit more in advance. Binding is basically the session between the client and the server, and it carries on throughout the connection, and it's like a context and session manager. It has any variables that are stored in the context, any security consideration are loaded onto it and are implemented on it throughout the connection, and specifically it also has authentication, which is what we care about. So in terms of the message flow, we have a map request between the client and the server, then a response to get the endpoint. Then we have a bind request, a bind response, and then an RPC call and its status. And we'll see how exactly the binding evolves over time with authentication in a bit. Zooming into how RPC is implemented behind the scenes or programmatically, on the client side, the client doesn't know or doesn't see any change in behavior. It just calls a function and gets a return. Behind the scenes, the function actually doesn't do anything. It just passes control to a function called NDR client call, which is implemented in the RPC runtime or RPC34 DLL. That's what is loaded to each and every RPC client or server process, because that's what actually handles all the RPC logic. Inside the RPC runtime, it's responsible for marshalling parameters, and that's just a fancy name of taking all the variables that or arguments that are passed to the function and making them network safe and passing them, connecting and resolving to the remote endpoint, doing the binding, authenticating if it needs to, and actually sending all the data. On the server side, the RPC runtime listens, of course, on all endpoints, and marshals any parameters that it receives to make them, again, binary representation that the function, that the server logic can handle, perform any necessary access checks, authentication, etc., and eventually pass control back to the server logic. Once the server logic finishes and the client and the function returns, the RPC runtime is then doing the whole process backwards to get the data back to the client. So that's it for RPC overview. Let's dive into authentication. So like I said, authentication is passed over the binding, and it's just another chunk of data that we just add to the packet of the RPC binding. And in this case, we have a snippet from Wireshark with authentication info for NTLM. But it could have been Kerberos, it could have been any other protocol that Windows supports. There are multiple of those, but NTLM, Negotiate, and Kerberos are the most commonly used ones. In terms of NTLM, in case anyone isn't familiar, NTLM works in a challenge and response model. So the client that wants to authenticate sends a message to the server says, "Hi, I'd like to negotiate NTLM." The server responds with the NTLM version that it agrees to use, and a challenge, which is a random blob of binary data, which the client then needs to encrypt with the shared secret. In this case, that's going to be the password hash, and send back to the server. That way, the server can check the encrypted data, see that it's the same as the secret, and that means that the client is who they say they are. But that's another leg. So in this case, instead of just having a binary request and response, we also have a third packet called auth3, which carries that challenge response data. We also saw it in the pickup. It's the last one here. And just it's useful to remember because if we want to implement a relay server, we have to implement all the steps of the binding. Now, RPC has a very unique interaction with authentication because it doesn't care about it by default. All RPC calls by default are unauthenticated. Neither the client nor the server need to use authentication, and it's not encouraged or enforced by any way. If the server do want authentication support from the RPC runtime, they have to set it manually with a unique call to a function called server register authentication of info, and tell the RPC runtime which authentication protocol to use. So it's not just you just turn it on, you also have to say which protocols you want. Kerberos, NTLM, Negotiate, Secure Channel, etc. On the client side, even if the server registered authentication info and a protocol, no one is forcing the client to authenticate. The RPC runtime doesn't care. And only if the server specifies a unique flag called RPC allow secure only then will RPC runtime reject unauthenticated calls. Otherwise, they're going to pass through, and it's the server's job to make sure that the client is authenticated if it wants to. So we talked about how the server has to call a specific function, and specifically, authentication in Windows is implemented in something that is called SSPI, or Security Support Provider Interface. Basically, all the various authentication providers like Kerberos, NTLM, etc. They all are implemented with the same interface, the SSPI, so that no unique logic is needed to be implemented to call each and every one. They can all be called the same way interchangeably. So when the RPC server tells the RPC runtime to use a specific provider for authentication, the RPC runtime just loads the corresponding SSPI DLL. This is done through the SSPI SRV DLL, which is what manages the SSPI, and it just loads specifically. On the client side, the clients that wish to have authentication during the calls and the binding have to call a specific function called binding set of info. Inside, we can have the binding handle, which is what represents this, the session, the RPC session between the client and the server. And we also have the authentication service, which is the protocol like Kerberos or NTLM, and the auth identity structure, which contains information about their credentials themselves that they must acquire. Now, in terms of flow, like I said, calls don't have to be authenticated, and there's no support by default. If a client were to use the binding set of info on an RPC server that didn't use it, they're going to get an error because the RPC runtime doesn't know what it means. So only after a server registers authentication info will the client be able to authenticate like normally. In terms of securing the authentication, that is defined by something called the authentication level. There are 6 of those, and those are defined by the client. So it's part of the client call of set of info, which just means the level of security that we have with the authentication. Of course, the lowest level is none, no authentication. But then we have level connect, which just means authenticate. And then we have call and packet, which just tell the RPC runtime how frequently should the authentication occur, whether it should be on just the start of the session, that's connect, or rather on each and every subsequent call. Then we have the more interesting flags, which are packet level packet integrity, which signs each and every packet with a secret made from the binding to make sure that there is no data tampering on the way. And lastly, we have packet privacy, which also signs the data, but also encrypts it. So just the client and the server can decrypt the RPC data and view it. Of course, Microsoft recommends that everyone implements their RPC servers with packet privacy, but we are interested, obviously, in level connect because there's no verification, there's no checks, and that just means it should be reliable. So, how do we find victims? Now that we know how our RPC authentication works, how it secures the connection, how do we find some suckers to hack? For that, we have a very easy way of finding all the RPC binaries because they have the unique trait that they have to import logic from the RPC runtime. So we can just iterate over system32, find all the binaries that use it. Then we need to use some sort of script to parse all the calls to register authentication info or set of authentication info to find all those that use authentication service NTLM or negotiate, which allows us to use the NTLM, and of course authentication level connect. In my case, I used a script with IDA Python. A few years ago, we implemented an RPC toolkit to help with research over MS-RPC, and I just modified it a bit to be able to check the authentication functions, and then hopefully we can have some profit. In our case, our profit comes from Windows Remote Registry, which is our victim of the day. It's implemented with an RPC interface with a UUID, and it also has a well-known endpoint called WinReg over SMB. Its RPC server implementation is in regsvc DLL. It's run as a service, which is not turned on by default, but we don't care because we are tracking the client. The client side is implemented in ADV API 32 DLL, which is kind of curious because it means it's just part of the Windows API and not in a unique DLL for its logic. And why is it special? Inside, we can have a single function that has two calls to RPC set authentication info. One time is for the ASCII version, and one time is for the wide version. But we don't really care about that definition because it only changes how the strings are implemented. What we care about is the authentication level. Auth info A uses authentication level 2, which is connect. Auth info W uses packet privacy. So what we need to do is figure out when or how it calls level connect, because that means we can hack it. So if we take a look at the call stack, both those functions are called from a function called base bind to machine, which is an internal function, which in turn is called by reg connect registry X, which is an export of ADV API, and also by reg connect registry W, which is a documented function on MSDN. It's basically what you use when you want to connect to a remote registry. So anytime a machine is using ADV API as the RPC client for remote registry, which is all the time because that's the Windows API for it, it's going to go through base bind to machine and then eventually through set of info, either W, which is the secure version, or A with the unsecure version. What we need to figure out is how to reach the insecure version. For that, we analyze the function itself, and we can see that by default, it uses the RPC traffic and binding over named pipes, which is found, can be seen here with the binding builder regcon named pipe. I think it's my name. It's not really documented, or it doesn't have a symbol in the debug file, but it's very easy to see the string afterwards. But if the RPC authentication or the connection fails over named pipes, it has a fallback policy, and it uses and tries to go through all the other RPC transports, and that's in the function array. So it just iterates over the array and tries to use various other structures to connect over remote registry until it eventually succeeds. And what's interesting is that the call with the named pipes, it's secure, it uses packet privacy. All the other calls in the fallback policy are insecure and use authentication level connect. The transport protocols that they use SPX, TCP, NetBIOS in 2 versions, and IPX. And all of those are just mumbo jumbo, right? I haven't mentioned them before because they're obsolete. No one is using them, no one should be using them, and I don't know why it's baked into the RPC client. Only TCP is the one that should still be used, which is pretty cool. It means someone sometime in the past probably implemented that and forgot to fix it. And of course, like I said, all the fallbacks use authentication level connect, which is insecure and very good for us. So in terms of attacking this, we need to have some sort of machine-in-the-middle attack. We have to be somewhere between the client and the server. And the client has to connect to our machine via for a remote registry. The RPC runtime will try to use SMB because that was implemented. We'll fail that connection. We'll say that it's not available. Then they'll try to use SPX. We'll also fail that connection because no one uses SPX. And then we'll try to go over TCP, which will allow because TCP is a commonly used RPC standard protocol. It's not suspicious. It's available in every network. We want to be able to use TCP, and we'll allow it. The client will start the binding and send their authentication NTLM negotiation message. We'll pass that back to the server. The server responds with the NTLM challenge. We'll pass it back to the client and say, yeah, we're going to bind to you. Here's the NTLM challenge. Please acknowledge. And the client is going to authenticate back, send the challenge response, and we'll relay it. Because we use authentication level connect, there's no checks on the integrity of the data, and that's why it's vulnerable on the client side. we can't relate to any server that actually requires packet privacy because it encrypts the data with a secret that is derived from the password and the session. So because we don't know it, because we do a relay attack, and we don't really want to crack it because that's not really reliable in real life. So we have to find some server that is not open or that allows authentication level connect. So we can't use the common lateral movement protocols like the service control manager or the task scheduler. And surprisingly, we also can't use the WinReg RPC server. It, during the binding, it checks the authentication level and it fails any connection that doesn't use packet privacy with an access denied. So my guess is someone sometime in the past already found a vulnerability over the Windows Remote Registry on the server side that it uses a less secure authentication level, reported it, but no one looked at the client till now. So that's what we have here. Okay, so where can we attack? We can attack the ADCS server. ADCS stands for Active Directory Certificate Services. It's basically an additional form of authentication where you can use certificates instead of passwords and secrets to authenticate. And the ADCS, there are multiple escalation techniques against it that are documented. What we're interested is its web enrollment service. It's basically like an HTTP portal that you can use to authenticate against and get a certificate. And on some configuration, the default configuration, it allows for insecure authentication. So it's a very common escalation target in the domain. And that's what we're going to do. So the victim is going to somehow connect to us over Connect Registry. And they're going to share the credentials. We'll relay that to the authentication to the ADCS server and get back a certificate. The cool part about this is that the certificate is persistent. We don't have to go through the relay process again and again and again for each operation. We can just use the certificate each and every time on every other access code that we want to use, and we will be considered as the victim user. So that's the attack flow. But words don't mean anything. Let me show you how it looks like. So on our demo environment, we have our victim. We have, we have our domain controller, and the domain controller don't have any user besides the user and the administrator, because it's a demo environment. Let's start our relay server. And it's implemented over the in-packet relay server. I had to do my own implementation or just add implementation because in-packet doesn't support the TCP RPC server. So I had to add my own. But I'm not going to add it to the in-packet logic because I'm not a developer. This is spaghetti code. It's going to be available on GitHub, but don't expect it to be anywhere officially. And so let's use our victim. Let's tell it to connect over a Connect registry. This is just a sample implementation. It's not any Windows component, just a program I made. And we're going to see it starts to authenticate. It tries to log in. We relay that back to the ADCS server and get a base64 certificate of the certificate, which we can then use. Let's close our client. Open Python. And then we can just paste it into a file. And we can have it here. Then we can use a tool called Certify, or basically anything else. But for demo purposes, let's use Certify to open an LDAP shell on the DC. And then we can add our own user to the DC, because in this demo I used a domain admin. But just for demo purposes, we added our own user. And we can see it on the DC if we refresh the data. If it would refresh. Okay, never mind. Just trusting it works. Let's see. Yeah, there it is. There's our hacks. This is for, of course, a demo. This is, of course, a demo environment and purposes. In real life, you'd probably use it on a different server. It's not reliable to have a domain admin just connect to you willy-nilly. So in real life, you probably have to do a few more steps to get domain admin, but you could probably relay to a different server that the user has privileges on. So I showed it on a random program I made that uses WinReg, but who are the actual users of this Windows API in Windows? What components use it? Obviously, we have the regedit client and the registry implementation, but also we have stuff in the ADCS environment itself, in searchutil, in distributed file system servers. All of them, when you have multiple servers available, they call each other over remote registry to query for parameters. So in a domain environment that has multiple ADCS servers or DFS servers, that's going to be called every time they start up properly, or even a bit more frequently. So using any poisoning attack to get machine in the middle, it might be possible to have a reliable way of getting machine credentials. Also, surprisingly, we have the task view and task kill software components in Windows that are commonly used. If you use them on a remote machine, they're going to call eventually a remote registry because they can. And I think the most interesting one is the Windows Event Viewer. Similarly to WinReg, the Windows Event Viewer has an option to connect to a remote machine to query its event log. It does so over RPC as well with a different interface called MS-Even or Even6. And with a quick Google search showed that there's a lot of activity revolving around it. A lot of admins are asking how to use it or issues regarding it. So it is a viable target in network attack scenarios and pen testing. The event viewer itself is implemented as a console for the management console in Windows, MMC-exe. And most of its low-level logic is implemented in a DLL file called ELS-DLL. Specifically, it's also, when you connect to a remote machine, eventually ELS-DLL has a call to remote registry to load all the data. So in terms of exploitation, we have the classic machine in the middle NTLM relay if someone uses it sometime in the organization. But we can also abuse a very cool trait of the fact that it's implemented over the management console, is that when you type event viewer on your machine, it's actually a shortcut. And that shortcut is for MMC-exe with the console file. And MMC-exe has the option to connect to a remote machine on startup. So if you just modify this shortcut, we can have a pseudo-consistent coercion attack to cause outbound remote registry connections. We can also obviously modify the registry to load a modified ELS-DLL, but that's a common hijack technique, and it's not really related to RPC. What's interesting about this approach is that to modify the shortcut, we need to have some sort of administrative privileges. But to bypass the patch for this CVE, we also we can also use administrative privileges, because the CVE for the patch for this CVE implemented a new function called calculate connection flags, which checks the registry for various verdicts. And specifically, we have a flag called transfer fallback policy. If it's set, then you have the fallback. If it's not set, by default, you don't have the fallback, and that's the patch Microsoft made. So any attacker that can set the event viewer backdoor can also set the transfer policy bypassing the patch. I saw that after Microsoft patched this vulnerability 2 weeks ago. I discussed this with them. They said, yeah, it's by design. It's a documentation issue. It's not really a vulnerability. But they're going to update the documentation for the functions for that. Now let's talk briefly about the disclosure process. And remember, kids, give accurate descriptions, because it took me half a year to get the CV accepted and even a bit more to get it batched. Because I initially opened the disclosure in February this year, and I said it's on Registry X, and I gave them only a half-working POC without ADCS, and they said, yeah, it's not an issue. Registry X has a flag that prevents fallback. We're going to update documentation, that's it. But they disregarded the fact that Reg Connect Registry W calls X without the flag, and that's what is usually used. So I reopened the report with a better POC with the ADCS relay, and it was eventually confirmed and patched this month as CV 2024-43532 as an elevation of privilege vulnerability with a score of 8.8. So yeah, give accurate description, it will save you tons of time. That's basically it for WinReg. Future research idea, I think that we can look for more reliable RPC clients. Unlike their server counterparts, I think they're a bit more overlooked, so we might find more RPC client victims. And also, I think it might be possible to create a more reliable coercion attack, like similar to Petit Potam or the Potam class attacks, on the Windows components that use WinReg, like DFS, like ADCS, etc. That's it. Thank you for listening. Any questions?